Okay, good morning, everyone. Welcome to the Joint Astrophysics Colloquium. I'm pleased to introduce our speaker, Martino Marisaldi, who is now professor at the Department of Physics and Technology of the University of Bergen in Norway. Martino is a longtime friend, a colleague from the Agile former scientific team, and he has played a leading role in advancing the study of impulsive transient phenomena, both from cosmic and terrestrial origin. Martino graduated and obtained his PhD at the University of Bologna and worked at the INAF's Bologna Institute, now OAS, from 2004 to 2016. And since the very beginning of Agile, Martino has played a crucial role in scientific activities related to the calorimeter on board the Italian satellite, and his research initially focused on gamma ray bursts until he realized that our instrument, originally designed to observe cosmic signals, was also able to detecting bursts of gamma rays originating from our planet, the so-called terrestrial gamma ray flashes. And his studies in this field have been fundamental in improving our understanding of the nature and phenomenological characteristics of these impulsive events, lasting only a few microseconds and associated with the most intense thunderstorm activity on Earth. Now, one of the leading experts worldwide on TGFs, Martino and his team have recently secured a significant ERC advanced grant to conduct an unprecedented studies of these still unknown transient phenomena. Okay, before giving the floor to Martino, I would like to remind you that you have the opportunity to ask questions and make comments at the end of the talk. For those in attendance, a brief coffee break will be held at the conclusion of the seminar, so you are invited to join us. And for those joining remotely, you can write your questions and in the chat, and I will read them at the end of the seminar. So I'll hand it over to Martino. With this talk, terrestrial gamma ray flashes, other fantastic beasts, and where to find them.
Thank you, Giovanni. And first of all, I want to thank you very much for inviting me here today. It's just a pleasure to be here again, where I had a lot of meetings in the early start of my career, a lot of discussion. And so I could also get the thrill again of taking bus 509 to get here in a day of strike. So it's been nice coming back. So now let's get to today's topic. Yes. Terrestrial gamma ray flashes and other fantastic beasts. You will understand soon what I mean by fantastic beasts. So let's go on. If this is working, it was working, but come on. Yes, so this is a slide that I designed more than 10 years ago, the first time I went to Norway. So, and I was pretty proud of it. What is the point here? In the early 70s, the Vela satellite constellation was built to monitor Earth because it was designed to detect nuclear explosions in the atmosphere. And luckily, they did not detect any nuclear explosions, but they found some weird signal that was later established to be of cosmic origin. That was the birth of gamma ray burst science. A decade later, the BATSE instrument on board the Compton Gamma Ray Observatory was designed exactly to detect and study cosmic gamma ray burst, which it did properly. But in addition to it, in 1993, they detected also some weird signal that later was established to be of terrestrial origin. So, designed to do gamma ray astrophysics, they also started the observational field of high-energy atmospheric physics, discovering terrestrial gamma ray flashes. So, it was the beginning of the 90s, and terrestrial gamma ray flashes stay here, basically. This is what I call the zone of high energy and upper atmospheric transit. Why a zoo? Because there are so many different beasts, so many different animals. Terrestrial gamma ray flashes are high energy transients, but in the beginning of the 90s, also a lot of optical transients were discovered on top of the thunderclouds. It was mostly elves, halos, gigantic jet, red sprites. So there is an entire world going on above the thunderstorms and up to the ionosphere. And actually the top question is, what is the role of these beasts and of energetic particles produced by the thunderstorms, actually, on the geospace? This is the question that intrigued me. So, since we are in an astrophysics institute, and this is supposed to be a joint astrophysical colloquium, I want to put in context what I study in the more general field of time domain astrophysics. So this is kind of a well-known sketch showing the various variable sources. You have the luminosity on the y-axis and the typical variability time scale on the x-axis. And here above is the subject of study of Batsy. So very high luminosity on a variability time scale, say, of the order of the second, more or less. So what, if we want to place terrestrial gamma ray flashes in this plot, I tried to do it for fun, and it turned out to be down here, actually. So from observations, we basically assume that we have about 10 to 18 photons at source with a pretty high energy, average energy of about 7 MeV. So if you do the math, it ends up that a typical TGS adds up to about 1 megajoule. Total energy in gamma rays, which is not that much. It's about 240 kilocalories, which is basically the calorie intake of a Big Mac. The point is that this Big Mac is digested in a few tenths of microsecond, and all the energy content is delivered to space in high energy gamma rays, above several MeV. But in the end, okay, of course, these are very close by sources, so they appear bright by but their intrinsic luminosity is uncomparable with astrophysical sources, of course. So why should gamma ray detectors designed for GRBs be bothered about this? Well, the point is that when we calculate actually the peak flux of these objects and we put them in context, we see that the peak flux of TGFs is well above the threshold for gamma ray burst detectors such as Batsy or also Fermi and several more. So actually, cosmic gamma ray burst detectors are perfect instruments to detect also TGFs. And in fact, they did it, and at least 4 of them were pretty successful in detecting TGFs. Batsy, as I mentioned, they made the first discovery of TGFs. Note that they detected just 9 TGFs per year. So in the beginning, TGFs, terrestrial gamma ray flashes, were thought as really weird, rare phenomena once in a while. So in all Batsy lifetime, they detected 70 TGF, more or less. Then RESI came, and they detected 350 per year, despite a much lower effective area. So what's the point? Trigger logic. Batsy triggered on 64 milliseconds timescale at minimum. These are phenomena that are significant on few tenths to few hundreds of microseconds. So only the brightest ones could make it to trigger Batsy. RESI had no trigger. They just downloaded all the photons and they ran a search algorithm offline. So they, despite the much lower effective area, they could actually get everything that was in the data. Same for Fermi. When it was working in trigger mode on 16 milliseconds, they just caught about 100 TGFs per year. While after they enabled continuous data acquisition, they really unveiled the gold mine, discovering about 800 TGFs per year. And same for Agile, despite, again, much lower effective area. So I will not go through all the discoveries made by these instruments, so because I only have 45 minutes, so I need to apply a selection, and this selection will be based on my personal interests. So I will focus on ASIM and on Agile and what came later. So just to give some reference frame about the phenomena, what it was known until recently. TGFs are short, few tens to 100 microseconds, more or less. Energetic, average energies is in the MeV energy range, so they are harder than typical gamma ray bursts, in fact. They are associated to lightning to some extent. We will discuss later a little bit more in details how is this association. They are typically produced near thundercloud top. They are bright, but their intensity scales as a power law. So the question is, they are bright, yes, but where is the threshold in brightness? Do we see all the populations or not? I will try to give an answer to this question as well. Concerning the physical mechanism at the basis, there is still some discussion, but there are some building blocks where we have more or less a consensus, the community has consensus. So what are these building blocks in the physics of TGFs? Key concept, runaway electrons. In an electric field in the atmosphere, if you have a free electron above a certain energy, the friction force that it receives by the atmosphere can be lower than the force exerted by the ambient electric field. The net result is that the electron accelerates. And if this acceleration takes place over a sufficiently long distance, then this electron can become relativistic. If it becomes relativistic, then it can emit gamma rays through Bremsstrahlung. And this is exactly what we think it happens. But again, one free electron is not enough to justify the huge flux of TGFs. So we need something, we need an amplification mechanism. Actually, we need two. The first one is the so-called relativistic runaway electron avalanche. Through Moller scattering, it was understood that energetic electron could knock on other electrons that could actually undergo the same process. The net result is basically an avalanche of runaway electrons that create new runaway electrons. But this can account at most for a multiplication factor of about 10 to 5. So we don't have enough electrons with this mechanism to justify the huge flux that we see from space. So something is still missing. And what is missing is believed that it's the so-called relativistic feedback. What is? Well, basic physics, again, you have electrons undergoing Bremsstrahlung, so there is a huge production of particles. Some of these photons produced can travel isotropically because they are insensitive, of course, to electrostatic field in thunderclouds. So that can travel back to the initial region, starting region, basically making new seed electrons that can still undergo avalanche. Same can happen with positrons coming from Bremsstrahlung and per production. Positrons would not multiply, but they would travel the opposite direction, further seeding the avalanches. If this mechanism is modeled, then you realize that it can account for a multiplication factor of up to 13th order of magnitude. That's a huge, and that's basic physics. There's no need for new physics. So we believe that these building blocks allow to explain the magnitude that we see for TGFs. What is not explained and what is not clear yet, having still many things, of course. So how these production mechanisms are actually coupled together, and what is the role of the large-scale electric field in thundercloud? What is the role of the dynamic electric field coupled to lightning, propagating lightning leaders? We said that TGFs are associated to lightning. A lightning is associated to an electric field which propagates. So it's a different story. it might well be that both mechanisms are at play, and this is actually what I most think. And again, what is the relation between TGFs and lightning? At what stage of lightning production gamma rays are produced? And can you have TGFs without lightning? Question mark. How many TGFs are there? Is it rare? Is it not? According to the measurements, it looks like that threshold and instrument sensitivity plays a real important role. Is this true? And in the end, this question number 3 has an impact, because depending on how many TGFs we are there, we can envisage different impacts on the atmospheric environment. So this is basically what I've been busy working on in the past 15 years, more or less. Why is this important? Let's see, how can I... Okay, yeah. So these are TGFs detected by RESI, superimposed to the yearly variability of the lightning activity, okay? So why this might be important? So there are 2,000 thunderstorms active at any given instant on Earth, for a total of 45 lightning per second, more or less, which has a large impact in terms of natural hazard. So lightning itself is a very complex phenomenon, difficult to model and difficult to observe in situ, and basically impossible to reproduce in the lab. So energetic radiation production appears to be tightly linked to lightning activity, which is so pervasive. So I think it is natural to ask oneself, try to understand this phenomenon coupled to such a pervasive phenomenon like lightning. So now, let's go back to the observations. I'm an observational guy rather than a theoretical guy, so this is my territory, actually. We said that we can observe TGFs from space. What I show here is a schematic view, artist impression of a TGF, okay, plus other beasts. You can have downward TGFs, you can have the so-called gamma ray glows. A gamma ray glow, just to give a short definition, is basically a long duration emission. So it's not a transient, it's not a short transient, it's more a glowing that lasts a fraction of seconds up to several seconds, just to give a context. Okay, we said that you can observe TGFs from space. What are the advantages? So, well, large field of view, long duration of the measurements. We had Agile satellites measuring TGFs for 17 years. And a large geographic coverage. You basically can cover the full world. This is good. What are the cons? It's expensive to make a satellite. You cannot choose where to fly once you have launched. And it's far from the source. So you are limited somehow in your sensitivity. And it cannot detect the so-called gamma ray glows. So how TGFs are related to glows? This is a question that cannot be answered by satellite measurements. So far, there are thousands of TGFs cataloged by the key players in the field: Agile, Fermi, and now ASIM. As an alternative, or again, we can detect, come on. Yes, we can detect TGFs from ground. It has been done. There are way less detection, just a few tenths of TGFs detected so far. What are the pros? Well, large area detector. Actually, these TGFs, the best results so far have been detected using cosmic ray detectors like the telescope array. You can co-locate other observatory, other instruments, mostly in the radio wave to measure characteristics of the associated light. This is good. The problem, what is that usually the thunderstorms will not collaborate with you. So if you have an instrument there, not necessarily a thunderstorm will pass over your instrument. So you are limited to short and sporadic observations, limited by chance, basically. and you cannot follow the target. As an alternative, you can do observations from aircraft. What are the advantages? You can follow the storm. You can go where the storm is. You can revisit the target if you are able to tell the pilot to go back. And you are much closer to source, so you are more sensitive. You can detect if there is actually something below the detection limit from the aircraft. The limits, again, short and sporadic observations. Sometimes your aircraft will have to go back. And you have a limited field of view. That's a drawback of getting closer to the source. It makes sense. There has been a flight campaign in 2011 named ADEL, led by the University of Santa Cruz. They had more than 30 flight hours, and they detected one very weak TGF. So this basically killed the field of aircraft observations of TGFs until 2023, until the Aloft campaign, and I will go back to this. Okay, now, again, many different satellites detecting TGFs, but I will focus from space on two things, on two missions, Agile and ASIM later. Why Agile? Well, because it's my first scientific love, as written here. So I grew up scientifically working on Agile, and this basically was at the base of my career. So I'm deeply thankful to Agile and the Agile team. What is Agile? It's a small mission of the Italian Space Agency dedicated to gamma-ray astrophysics. People would kill me if I say this, but it's basically a very small Fermi. Very small, yes, because the payload, the scientific payload, is basically a cube of 60 by 60 by 60 centimeter, and at the bottom of which we have the so-called mini calorimeter. And it was called mini because we could not afford, because of constraints, mission constraints, to have a proper calorimeter with many radiation lengths. So the stopping power was limited, and it was made with very coarse position resolution, I would say, just 30 very long scintillating bars. So we tried to compensate these technical limitations, making the data acquisition strategy the more clever, as clever as possible. And we did a very important thing, and it was to include trigger window on 300 microsecond time scale. That was not expected because this was an instrument designed for cosmic gamma ray bursts. So it was completely exploratory to include such a short time window for the search of cosmic gamma ray bursts. People were thinking about primordial black holes, annihilation, things like that. It turned out to be fundamental for the detection of TGFs because their time scale exactly match this 300 microsecond time scale. And so, in addition to doing a very good astrophysics, it was also one of the three key player mission in terrestrial gamma ray flash science. And I kept in my hands that instrument, so I'm very proud of it. And when it started detecting, when we realized that it was successful in detecting terrestrial gamma ray flashes, that triggered my interest and basically tweaked my personal interest towards this side of atmospheric sciences. Okay, so I will just briefly go through the main contributions to TGF science from Agile, because I think this is the right place to present this. And first of all, right from the start, we realized that the energy range of terrestrial gamma ray flashes extended at least to 40 MeV. And this was doubling the previous range that was set by RESI. For a very simple reason, the high energy range of RESI was 20 MeV. So TGFs had, at maximum, 20 MeV energy range. Then it came Agile, which had an extended energy range. And we realized immediately that TGFs extended to much higher energies. And this was basically the paper that marked the entry of Agile into the TGF business. Then we also realized that we were able to localize TGFs from space using the silicon tracker. So this is a paper I've been very proud of, despite actually we were doing localization with one photon. So I would say that the accuracy in the location was not that high, but it proved a very interesting possibility. Then we made a correlation study with lightning flash ratio, and we realized that it's not constant. So different lightning emitting region, lightning producing region has a different TGF to lightning ratio. So this was puzzling, and it's still puzzling. And this the results that we were the first to publish was actually confirmed both by Fermi and later by Asim. So it was an important result. Then we put the Agile results in the frame of current observations, and we realized the so-called first Agile TGF catalog. And doing so, we realized that we were biased. We were biased towards long TGF, and we tried to understand why. And the key point was that the short TGFs were triggering the anti-coincidence shield on board Agile, so that actually we were not getting any photon. So the TGFs are so bright that they make the anti-coincidence shield on board Agile fire continuously, so that the detection of photons is completely depleted on Agile. When we understood this, we tried to disable the anti-coincidence shield for the mini calorimeter on board Agile. We worked with the people in charge for the configuration, so it's been a very nice job. We finally made it, thanks also to Asi, and what you see here is the cumulative number of TGFs before and after we changed the configuration. So this was absolutely successful, and we moved from 10 TGFs detected per month, maybe less even, to 3 TGFs per day. So we definitely boosted the TGF detection capabilities, because also we were getting these short TGFs that we were rejecting before. So this was extremely successful, and allowed us to collect more than 5,000 TGFs, which are now available to the community as a catalog organized at the Space Science Data Centers of the Italian Space Agency. Last contribution that I want to mention is that a peculiar thing that discriminates Agile with respect to the other mission detecting TGFs is the very low inclination orbit. It was designed for gamma ray astrophysics, so the best place to go is a low inclination orbit. So you get a small, as low as possible and as constant as possible background, which is good for gamma ray astrophysics. It's good also for TGF science, because most of the lightning emitting region and TGF emitting regions are located near the equator. So it's good to be there. So good that we were able to detect the same storm, TGFs coming from the same storm, up to several orbital passages. It means that it tells you that TGFs are an intrinsic part of the dynamics of the storm, because you can detect them after several hours during the development of the storm. So now, this is the main result that I want to summarize about Agile. Then I want to get to what is the current benchmark for TGF observation from space. And this is the Atmosphere Space Interactions Monitor mission, so-called ASIM. Where is ASIM? ASIM is here, attached to the external facility of the Columbus module. And here is a closer portrait. This picture is really beautiful. Here we have the Dragon crew that brought ASIM, actually, and here is ASIM. So, what is ASIM in terms of payload? Okay, first of all, what is ASIM? Is a mission of the European Space Agency dedicated to Earth observation, and it's led by DTU Space in Denmark, the University of Bergen, the group where I come from, and the University of Valencia, Victor Reglero's group, just to make it plain for the astrophysicists. What is ASIN in terms of payload? It's basically a coded mask gamma ray burst detectors swapped and pointed towards the Earth to make it plain, plus an optical instrument, which was, by the way, fundamental. So when it comes to the gamma ray detector, it's 2 layers, one layer of cadmium zinc telluride, coded mask, which did not really prove very useful, and a high energy detector, which is the workhorse for TGF detection. In addition to this, we have an optical payload where we have 3 photometers in wave bands which are fundamental for understanding the physics of lightning. This 777 nanometer is a line emitted by a hot leader, propagating leader, while this is an ultraviolet band related that can be used to detect ELS, and this is another blue line which is more related to streamer activity. These different components of lightning. So, what is the key point? The key point is the combination of the 2 instruments. For the first time, we have simultaneous X gamma ray and optical observation with high time and spatial resolution. So it's not true that the coded mask imaging is useless, but it did not prove to be a real breakthrough as I myself was hoping for in the beginning. But it was. I would rather say that the main science came from other things, and in particular from this combination of optical and gamma rays. For example, we were able to investigate with ASIN the TGF and lightning sequence. So the science question, how TGFs are related to lightning, and at which stage of lightning production do you have the TGF production? So this is a sketch that we produced for our first press release shortly after the launch of ASIN, sorry. And where we, by investigating the TGF and the property of the optical pulse following the TGF, we understood that the TGF is preceding, or at least simultaneous, with the optical pulse, which means the optical pulse is actually marking a strong current pulse. So the TGF is produced before a strong current goes through the lightning. So actually before you short circuit the cloud. And this, just to summarize this is the most recent paper that deals with this. Here we have, this was a peculiar case study because we have a huge TGF. This dip, I think it's mostly because of saturation. It was very bright and very long. So long that we can be really certain that this current pulse producing the optical signals actually came at the end. So actually the current pulse is shutting off the TGF, marks the end of the TGF. And in the end, this is the best case, but we have many hundreds of TGFs with simultaneous optics that tells us the same scenario. TGFs are produced before or simultaneously with the onset of the optical pulse, which basically means with the onset of a large current pulse. Second thing that I want to mention is the relation between terrestrial gamma ray flashes and ELS. What are ELS? ELS is another kind of fantastic beast. These are emissions that come directly from the ionosphere, and they are expected to be, they are observed as expanding rings of ultraviolet light. And actually, it is not a real motion because it's due to the propagation of a spherical electromagnetic pulse that hits the ionosphere. It excites molecules, and you see the ultraviolet light when these molecules are just going back to the steady state. So for the first time, we were able to observe a TGF. Here you see the TGF, and then a strong ultraviolet pulse. You can see that this strong ultraviolet pulse is much faster in terms of rise time than the associated red and blue pulses. This tells us that it's coming unattenuated. So we understand this as a signal of a nerve. So for the first time, we have the observational evidence that TGFs and ELVs are related. But again, it's not the TGF that causes the ELV. It's the same lightning phenomena that is associated with the production of gamma rays and at the same time produce the electromagnetic pulse that triggers the ELV in the ionosphere. It had been predicted, but it had never been observed before, because without ASIM, it would have been impossible to observe it. And we made, I think, this beautiful video here, just to represent this phenomenon. Here are the gamma rays, and here is the ELVs. Again, it's not the gamma rays that produce the ELV. It's just that these are pulses that travel at the speed of light together, both the gamma rays and the electromagnetic pulse. And this was very good, so they liked it also as a cover page in Science, which, as you can imagine, gives us a very nice publicity, which is always good. So now I go back to my very first slide here about the discovery of TGFs. So shortly before the launch of ASIM, I modified this slide, and at the end of all the story about Vela, Compton, and discovery of TGF, blah, 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 I used to say, okay, now we are going to launch ASIM. So an ASIM is the first mission specifically designed to detect TGFs. So if things go the same way, what can we expect to discover from the astrophysical point of view? Actually, it worked, because yes, ASIM, of course, detected a lot of TGFs, and that was expected by design. It detected also some, not that many, short GRBs, and this was also expected, because for the same reason why gamma ray burst detectors can detect TGFs, okay? You still have a gamma ray detector in space. And what was not expected is that we were able to do also high-energy astrophysics science. So we were able to detect the first giant magnetar flare from an extragalactic magnetar. And the point is that despite being extragalactic, it was close enough so that many instruments were anyway saturated. These are huge explosions. When it happens inside our galaxy, that basically blinds out any detector. And there are people sitting here much more expert than me on this subject. So the point is that even in a nearby galaxy, this event was bright enough so that the main competitor, for example, Fermi, was heavily affected by instrumental effects. When you have a lot of instrumental effects, you cannot trust it much. The electronic design for ASIM was such that it was really tailored for the high flux of TGFs. So a lot of attention was made to minimize and take care of instrumental effects such as dead time and pileup. And the net result is that we detected this event without significant instrumental effects. And this allowed the Spanish group of Castro Tirado, in collaboration with us, to identify kilohertz oscillations in the giant. They did not like this as a cover page, but that's okay. It was useful anyway, because it went as a high energy picture of the week NASA ESAC archive. So this just it's a story that I'm very happy to tell, because we were able to do excellent science also in a field which was not the field by design of our instrument. So it's satisfactory, definitely. So did the investment in ASIM pay off? definitely, I would say, from the scientific perspective, it definitely paid off. And it was instrumental also because it paved the basis for the next endeavor that I'm going to talk about, which is the Aloft flight campaign. So what we did for this flight campaign, this is an aircraft campaign, the knowledge, and also part of the hardware, because we are flying basically a piece of ASIM, a spare piece of ASIM. What we did was directly influenced and enabled by our work on ASIM. What we did actually do, this is this aircraft campaign. how can I say, I can state that it set a new state of the art for TGF study. And what is Aloft? First of all, it stands for Airborne Lighting Observatory for FEX and VGFs, where FEX is Flies Eye GLM Simulator, so it's 3 nested acronyms. That's very, very by the way. And this is a flight campaign led by the University of Bergen, our group, in collaboration with many institutions, including and making use of a high-altitude aircraft from NASA. So this is the high-altitude aircraft. This is a ER2, which is now in service as the NASA Airborne Science Program. It was a former U-2 spy aircraft, but now it's just doing scientific research. What is peculiar of this beautiful aircraft is that it flies at 20 kilometers altitude, so they have no fear in going on top of active thunderclouds. And this was instrumental for the results that we obtained. So the science question that we had in mind when we shaped this campaign is, first of all, is there a population of faint TGFs? And how extended in space and time are gamma ray glows? And what are the physical conditions of the thundercloud associated to glow and TGF production? And how TGFs and glows are related? Just remember that glows are long duration gamma ray emission, which are too weak to be detected by satellites. So there is no way you can answer this question from space. The methodology that we used was use a high altitude aircraft because we wanted to fly on top of the thunderclouds, as close as possible to the sources, to have a high sensitivity. And we wanted to chase the thunderclouds, go where we were expecting to see something. And, but again, remember that there has been only one previous aircraft campaign that detected one TGF in 2011. So we did not know if this campaign would have been successful. So just a few words about the payload. We followed a really multi-messenger approach in designing the payload, meaning that we had, of course, gamma ray instrumentation, both from us and from the Naval Research Lab. This is Eric Groove, basically, for the astrophysicists here in this room. We had an optical instrument, this so-called FEX. This is an imaging array of photometers. And so basically, with these two instruments, we reproduce the advantage of the ASIM mission, simultaneous optical and gamma ray observations. In addition, we have instruments for the characterization of the electrical environment. So we had an electric field change meter, and we had several field mills that were measuring the electric field vector, actually in 3 components, at the aircraft. Plus, we had a full suite of cloud characterization instrument provided kind of in kind by our partners from USA. We had 2 radars, and we have 2 microwave radiometers, so actually passive instruments and 2 active instruments. With this huge and very complementary suite of instruments, we made 10 science flights in July 2023, taking off from an Air Force base in Tampa, Florida. And we were able to travel basically in the Gulf of Mexico and down almost to Panama, basically. And of course, in Florida. With, in addition, a lot of coverage from ground-based radio instrumentation that was observing together with us. So this is just, I want to show you the landing of this aircraft just because it's beautiful. So this was taken at the end of one of the science flight, and this huge aircraft, you can see it does not have other wheels. So it just has two wheels, so it must keep a perfect balance. This is why there is a car chasing. It's called the chase car, actually. The car is chasing the aircraft, so this car is almost a sport car, running 200 kilometers per hour behind the aircraft. And there are two pilots for this mission. One is on the aircraft, the other one is in the car and tells by radio to the pilot on the aircraft how to work in order to keep the balance. And all of us just were queuing to get a ride there. Okay, it was just beautiful. Let's get to science now. So, what was the key asset of this mission? The key asset was that we had, one of the key assets was that we had real-time telemetry. So we were sitting in the control room, looking in real time at the gamma ray count rate, and when we were seeing something good, we could communicate in real time with the pilot and telling him to come back and scan the same region again. This proved to be extremely successful, and this is why we have this such a counter-shot trajectory. So what I will show you now is basically a video showing one of our most successful flights. I will not say anything, but the black line that you will see here basically is 6 minutes of data, and it's also represented here. Here you have the gamma ray count rate on board the satellite, okay, for these 6 minutes of data. You will see a lot of increase in flux, and you will see some red lines, purple lines. When you see purple lines, that's a TGF. So you will immediately understand that we have a good answer to the question, how rare are TGFs, okay? Here we come, in the party. Here we go. We go again, same region, and we see again. We go again, and we see close again. Here we go. Again, this is pretty active. See again. Lots of TGFs, lots of glows. This is just fantastic. We were not expecting this. This was a big mesoscale convective system out of the coast of Mexico. This is Campeche Bay in Mexico. And then we had to leave. Otherwise, the party would have gone on for a long time. So to me, this was just fantastic. And you can imagine how could I have been feeling. Actually, I was on the east coast of Italy having vacation with my family when this flight happened, but I was there in Tampa for the first flight when we detected the first glows and the first TGF. And okay, that was a satisfaction, big satisfaction, I must say. So, okay, this is the full 3 hours flight. You see a lot of gamma ray glows. These are a few seconds lasting gamma ray transients. Now I will just take a focus on this small segment here, and this is what we see basically. This is an artistic view that we proposed for the cover page of Nature actually, but this time we didn't make it because there was they chose the brain of a fly there. It was a scan of the brain. Very colorful picture by the way, but this is very cool in my view. And in addition, we could see that traveling the microwave and the radar gave us an understanding of the environment where this high dynamic emission was produced. Here we are passing over 3 hot spots that appears white in the microwave test, and you can see also in the vertical profile of the radar, we are really going through over convective cores. Each of them is about 8 kilometers. And when you go there, you really see brightening up and down in gamma rays. So this was really amazing for us. And again, fantastic beasts. If you take a very detailed zoom here, what you see is an oscillating behavior like this. This is a few hundreds of milliseconds long. This had never been observed before, and we named it flickering gamma ray flashes. So this was actually a discovery of the Aloft flight campaign, in addition to all this unexpected, highly dynamical behavior in gamma rays. And we found 24 of this. So this is a phenomenon which is there, but it's not bright enough to be detected from space, unless we look back to the first discovery paper by Fishman et al. And we see this guy that for 20 years I believed it was due to instrumental effects, actually. And actually, luckily, it was the first detection of a flickering gamma ray flash from space. So another discovery was that, again, we have a large population of weak TGFs. You have seen a lot of TGFs detected there. And here we prove it, just combining ASIM and Aloft data. This was the trajectory of Aloft. This was the passage of ASIM. During these 2 minutes, Aloft detected 6 TGFs. None of them was bright enough to be detected from space. So we already have a good hint that TGFs can be much dimmer than what is needed to be detected from space. Actually, we detected more than 100 TGFs. With these 100 TGFs and some statistics, we also made intensity distribution, source photon brightness distribution. We have, here we have basically log-log plot, where we have photon brightness and the rate of TGFs. And we can see that basically this is what the part of the distribution that can be detected from space. And we have all of this, which is in logarithmic scale. And here, the cutoff at low fluence is limited by our sensitivity. So we don't know how actually this distribution is going up here for low fluences. So TGFs is really a pervasive and low fluence phenomenon. So now, just to summarize, discoveries. Tropical thunderclouds glow with gamma rays for hours over thousands of square kilometers with a highly dynamical behavior. TGFs are much more common than previously thought, and only a few percent can be detected from space. And there are new fantastic beasts, flickering gamma ray flashes, and other things that I had no time to report, still under study. There are different phenomena which are not accessible from space. And this we were able to publish into 2 twin papers in Nature. And so what? What next? What we don't know, given this new state of the art, we don't know where are the gamma ray emitting regions. So we don't know if the dynamical structure is due to one single region, rebrightening up and down, or if it is different regions just popping up one after the other. And we don't know how these emitting regions are reshaped following a lightning discharge, for example. So basically, it's like listening to music without knowing where the music is coming from. And what do we need to answer this question, or to investigate this question, is imaging. We need imaging both in gamma rays and for the lightning. And thanks to these ideas, what do we want to do, in fact? We want to have another flight campaign, high altitude, using the NASA Air2 in the same place as before, because then we know where we can find our fantastic beasts. And we need an imaging system, gamma ray imager, and we want to build it with a pinhole camera derived from ASIM. And we need also to image the lightning using VHF interferometer. And for the first time, we want to do it directly on board, so we do not need to rely only on ground instrumentation, because we carry our interferometer together with us, and we image whatever we find below us. That's the idea. This crazy idea was awarded an ERC Advanced grant that actually started the 1st of October. Now I am the PI for it, We have basically the full Aloft team here embarked, and our team in Bergen, and we have already a flying slot for July 2028. So stay tuned for that. And with this, I thank you very much. I think I went over the allowed time, so I'm sorry about that. And I definitely want to thank the team in Bergen, the ASIN team, and the Agile team, and all of you for listening. Thank you.
I remember many years ago, maybe it doesn't apply to your science, many years ago, Jodoiwer was actually triggering from the Earth lightning with the gamma ray detector. Is this something that is still a good way to proceed, or basically with all these instruments is no more useful this kind of activity?
This triggered lightning activity is something that goes on. Actually, he was the first one using a pinhole camera with gamma ray detectors to image actually the gamma rays emitted from the downward lightning. That was a great job and inspiring. It's a little bit, it's not the same thing, because now with this system, what we propose is really to go in the natural environment with a triggered lightning. I mean, it's the best experimental setup that you can do with lightning in the end, apart from going and looking after them. So it's still an interesting way to go. We are in collaboration with people running a controlled lightning facility.
I have another question, just for, is there any evidence of difference of TGF with the latitude, or basically with the health latitude, or basically?
I had a couple of slides on this that I had to skip. I will just go there. Okay, yes. This is what was detected with ASIN. ASIN was good at doing this because it is on the space station, so it reaches up to 51 degrees in latitude. So it could scan for the first time the temperature zone. So the result, the bottom line is that there are few TGFs there detected from space, but if you look at the altitude of the tropopause, which basically means where you can expect the TGFs to be produced, at high latitude you have a lower tropopause, so the air is denser, so the signal will be more attenuated. If you keep this into account, you see that there should be a comparable TGF to lightning ratio also at high latitude. So the guess would be, if you go and chase for TGS with an aircraft, also temperate latitude, you should be able to see them. This is my guess, but nobody has tried it.
Thank you very much for your very interesting talk. Thank you. And I would like, I'm curious about the initial mechanism. It says that in your point 4 of slide 8, you said about the impact of chemistry and dynamics of the atmosphere. But is there, any information, hint about the rule of the atmosphere, the sense of chemistry and density and physical conditions? That would be very interesting to understand.
Yes, so this is a question which is actually still open. First, modeling based on the known rate of TGFs was done, for example, to estimate the impact towards NOx production, so oxide of nitrogen oxide, and that was basically understood to be negligible. Now we have seen that we have way more TGFs, but they are also dimmer. So if this can be relevant, I cannot answer. The chemistry of the atmosphere, the role of the chemistry of the atmosphere for TGF production is more on the, how can I say, what you need is density, because you need to do this avalanche of electrons, so you need your electrons to knock on other electrons. At the same time, too much density would attenuate, so it's kind of a trade-off. So, but that question is definitely still open. But one thing is clear, so gamma ray production is really strongly coupled to electrical activity. So when you have a large-scale electric field and you have lightning activity, you, at least when we're on the Caribbean where we went to fly, you always have gamma ray production. So it's a real component, important component of the convective environment.
So just may answer. And the fact that you said that the TGF, the flash is coming from the very beginning of the lightning, don't you think this may be due in fact to this aspect? I mean, the fact that when you start the lightning, somehow the electrons have more friction in the atmosphere, while once the lightning is established, there is a sort of a way from the beginning to the end of the flash that basically the atmosphere does not play any role. Do you think it's reasonable?
I think that the main point there is the interplay between the lightning leader electric field and the ambient field. That's a crucial thing. So you wouldn't have TGF, you wouldn't have acceleration if the electric field within the thundercloud is not large enough. So I think that the electric field is more kind of relevant for the production of TGFs.
Martino, reactor.
Flickering TGF. So what is a possible emission mechanism, a possible progenitor? It's
yes.
strange.
What I did not have time to report is that these are observed. Basically, they do not have an optical and a radio counterpart. So they are basically optical and radio silent within the sensitivity of our instrument. Basically, this tells us that they are not related to lightning leaders. Often we have a flash later, but several tens of milliseconds later, which basically means is an eternity in TGS point of view. So what we actually think that is happening is a large scale, but this is my conjecture at this moment, so not only mine, but it's not proven. We think that this is what Joe Dwyer, close to what Joe Dwyer long time ago called dark lightning. So basically a discharge process driven by the large-scale electric field, which becomes unstable mostly because of the feedback mechanism. This instability of the large-scale electric field basically drives this modulation of the electric field, which is reflected in the modulation of the gamma rays. At the same time, the electric field basically propagates downward in a sort of a wave. We call it relativistic streamer discharge. So this is one of the possible views, but the observational evidence is that it is not related to a lightning leader that emits optics and radio signals as other classical TGS.
First of all, curiosity, why a single wheel plane?
I have no idea. So actually, when it takes off, it has two wheels, and they are designed not to go under the wing. They just fell off. So that's by design. You should ask some engineering of the 60s, because this is pretty old aircraft.
Slightly more serious question is, I guess you're using a lot of meteorology science in your Are you providing any feedback to meteorology by your understanding of this phenomenon?
We have not done it yet. That's something that I have in
Are
mind.
they looking at you?
Say it again?
Are they looking at you? I mean, are they following your work to learn something about the...
I don't know. It's not so. I mean, we did not reach out to meteorologists yet, so we are more on the fundamental science point of view, understanding the phenomenon. This is one of the things to do. Reach out to the meteorologists, definitely. And of course, we have their help when we do this campaign. We have actually a team of meteorologists that helps us in the prediction, because a few days in advance we need to decide where to fly, and that is based on predictions. And then on this very same day, we basically have a meteor briefing every day. It's really interesting, the organization of this campaign, very fun.
Hi.
Hi.
Nice talk.
Thanks.
I have a question. Looking at the Agile map, did you think to invert the process? Thinking whether this TGF might be connected by our cosmic source. So we are bombed by cosmic rays. Did you try to correlate the appearance in the sky of the, so you have a strong cosmic source, of the source of cosmic rays, and the appearance of TGF? So you are bombed by cosmic rays in a bomb.
We didn't do that.
I
I remember there was one of the first papers claiming a correlation between TGFs and blazars, basically. But of course, cosmic sources, but when we talk about cosmic sources, what I have in mind is mostly cosmic rays. They contribute to produce free electrons that might undergo this process. But the cosmic rays that we need for triggering these events are not necessarily strong transient sources. We are continuously bombarded with normal electromagnetic showers are everywhere. And they are more than enough to produce the seed electrons that we need if we have a large-scale electric fields that can lead to this multiplication. So the key limiting factor is the large-scale electric field. The constant bombardment of cosmic particles just contributes to the overall seeding of free electrons. But whether you get a TGF or not is not driven by the seed source. It's more driven by the large-scale electric field.
Yeah, imagine like supernova and very strong bombing appearing in the sky.
I don't think it would be enough.
Questions over there?
It's not clear to me, when you have a TGF with this, do you always have an optical counterpart in a MIA instrument, or is it solid?
When we are sure that the TGF is within the field of view of Asing, yes.
Okay, and that happens in which time scale? The optical counterpart?
Well, it takes place, the optical counterpart is immediately after usually, or a few hundreds of microseconds later, usually when we see it. When it is a few hundreds of microseconds later, it's only a few cases, and I personally don't have a clear explanation for that. But when we are, on the other hand, when we are sure that the TGF is within the optical instrument field of view, we always have an optical signal.
And in which wavelength?
777 and 337. 777 is usually red associated to a lightning leader, basically, so to a hot channel.
Okay. And the slide before you show the correlation between TGF and S, you had, I think, a slide showing the TGF and then the optical. But the time scale on that slide was millisecond. I did not, I'm not sure it was very small.
In the end, the optical signal is a few milliseconds, yes.
Okay. Thank you.
You're welcome.
We working with gas detectors in space. Always panic that the IZ ion crossing the gas can start a deadly spark and kill the missions. It occurred many times in the past. About the previous question, not any special cosmic event, but one single ion of iron, could it be the seed of this spark?
considering this, the relation between cosmic rays and lightning also is highly debated. There are many studies that claims that actually the inception of lightning happens after an air shower, in condition of an air shower. It's a little bit up under debate also because the lightning initiation problem itself is one of the most relevant open issues in lightning physics. At the same time, I honestly think that the free electrons produced by a strong cosmic shower can play a significant role with TGS. We are working on that also, but I cannot say more than that now.
John?
Hi, very interesting talk.
Thank you.
Also an interesting phenomenon that I was not aware about working on a different field of astrophysics. My question is that since this is really basic physics, you need just electrons that are accelerated in an environment where you cascade. Can we expect that this kind of phenomena also happens not only in our atmosphere, but other atmosphere, like for example other atmosphere, other planets in the solar system? And if you can, anyone has tried to identify this kind of phenomena, and if there is any indication from the data that already we can obtain from the diversity of the atmosphere in our on Earth, to propose how much intense this phenomenon can happen in other, like Jupiter, Venus, I don't know.
There have been studies trying to model these avalanches in different planetary atmospheres. I don't have them clear in mind because I never focused on them personally, and so as far as I know, there are no observations yet. But someone has done some modeling on that.
Do you find some seasonal behavior of the occurrence of a TGS? Clearly, this tropical belt is the one that during season has the most stable situation for thunderstorm and so on. But have you seen something like that?
Actually, if you use a TGF detector from space, which is what you need to do this kind of studies, there is a very clear seasonal correlation that goes with the seasonal variation of lightning activity. It's focused on the equatorial belt going up and down. That's the intertropical convergence zone, it's called.
Have you found some difference? Because I heard somewhere in some outreach occasion related to meteorology that typically in thunderstorm happening at the end of the summer, there are more lightnings than during winter, for example. So this would be related to some, I don't know, property of the humidity, I don't know, of the atmosphere. So have you found some difference of TGFs happening in a certain season with respect to what are happening in the other season?
I don't think, we never tried so deeply because in the beginning we did not have enough statistics to do a proper job in this regard. And then there has been a lot of studies trying to figure out the meteorological condition more functional to the production of TGFs. And all of them boiled down to a little bit inconclusive results. The only common result is that high convection, high lightning activity, large number of TGFs, which is also what we see with the aircraft campaign. In the end, after 1 month of observation, we knew where to go, and we knew that we were going to observe TGFs there, because you just needed to target a high convective core in a mature stage thunderstorm, and you were pretty sure that we were going to get fireworks there.
You know, your talk was so interesting that
I had no idea what the time actually. So
we can continue to.
I apologize if
No,
I'm
no.
way over the.
Fine, very interesting talk. We can continue to question bombing the speaker during the coffee break. So please stay here. and thank you again.
Thank you.